Here's our setup. I've got my laser right here, which I'll turn on. It will shine into this tank that is filled with water. And then at the bottom of the tank, along the bottom of the tank, I have a mirror so that the light will reflect off the bottom of the tank. Let's turn it on and see what it looks like. Here's the laser up here, and between the laser and the tank of water, we can't see the laser beam because there is nothing that is scattering the light. We need some kind of particles in the air to scatter the light. In the water, I put some mop and glow, which causes the light to scatter, and it allows us to see the beam. But if I put some water droplets in the air, we'll be able to see the laser in the air as it moves into the tank. So here's a freeze frame picture from the video. I sprayed the water droplets in the air so that you can see the incoming laser beam as it enters the water. Then it goes through the water, reflects off the mirror at the bottom of the tank, and shines back up and leaves the water, and you can see it over here as well. So I'm going to add to this picture a bunch of notations. So here is my air-water boundary or air-water interface. Here's my incoming laser beam coming in this direction. It enters the water at the incident angle. Theta I is my incident angle, the angle that the light is incident upon the water at. And we see that we measure the angle with respect to the normal. So these dotted lines are the reference line normals to the water-air boundary. And we see that as it enters the water, we call this the angle of refraction. The light has changed direction. It has refracted. And we're going to talk about why that happens in a minute here. Then it travels through the water to the bottom of the tank. It reflects off the bottom, and I use theta prime to represent the reflected angle. And we know from the law of reflection that the angle of incidence upon the mirror is equal to the angle of reflection off the mirror. Then the light comes up here, and now the beam is, now it's called the incident angle on the bottom side of the water because it's incident upon the interface. It doesn't matter if you're coming from the air to the water or from the water to the air. The first angle is the angle of incidence, and the second angle after refraction has occurred is called the angle of refraction. And then here we see it leaving the water. I measured the incoming angle, the angle of incidence. I overlaid a protractor here so you can see the angle measurement. 46.5 degrees is my incident angle, and 33.5 degrees is my refracted angle. So light entering the water from the air, we see bends towards the normal. Here it came in at 46.5 degrees, and now it's 33.5 degrees from the normal, so it got closer. This angle right here is smaller than this angle up here. We say that the light bends towards the normal when it enters the water. Let's talk about why that happens. Here's a little movie that shows what is happening with the light, and I'm going to freeze it here in the middle, okay? And so here are the wave fronts coming down at a certain wavelength and a certain velocity, and because it's at an angle, we see here that this side of the wave front enters the water first. And so since the light has a slower speed in the water, it starts to lag behind. This part of the wave front that is not in the water yet is still traveling at its original faster speed, and so it tends to get ahead of the other part of the wave. And then once all the wave is in the water, all the wave front is in the water, then they're all parallel to one another again. But the result of this slowing down of one side of the wave before the other is that the wave changes direction. And we can see here, this of course is my ray that is drawn perpendicular to the wave fronts that shows the direction the wave front is traveling. And now the direction of the wave, or the direction of the light, has changed. And we can see here if this was air and this was water, it has bent towards the normal. Theta 2 is smaller than theta 1. As it leaves the water, the reverse happens. It bends away from the normal. And we say here, light entering air from the water bends away from the normal, and we can use the reverse reasoning to figure out why that happens. As these wave fronts are coming up, this part of the wave over here leaves the water first and goes faster now in the air and tends to get ahead of the rest of the wave. And then by the time the other part of the wave leaves the water, it's going in a new direction. And we see that the exit angle was the same as the entrance angle over here, and the incident angle on the water to air boundary is the same as the refracted angle over here. Let's make sure you realize that's only when this top surface and this bottom surface are parallel. So here you see as the light enters the new medium, in this case glass, the wavelength or the distance between the wavefronts becomes less. So lambda 2 here is less than lambda 1. We also know that the velocity of the wave has decreased because it entered the new medium. Remember, that's the reason why the wave changed directions in the first place. So the velocity is less and the wavelength is less. So I'm not going to go through the proof. You can see it right here. But what that means is the frequency does not change. So in other words, even though the wave has slowed down, the frequency is still the same. So if our eye was inside the glass or underwater, if this was water, that means the color of the light would not change. The frequency, remember, is the color. And so that didn't change. So we would still see the same color, even though the wave has changed direction and slowed down. Now we're going to introduce a new vocabulary word, and that is the index of refraction. And it's represented by the letter N, and it is the ratio of the speed of light in a vacuum over the speed of light in a medium, such as water or glass. So that's always going to be less than the speed of light in a vacuum. Light always slows down when it enters a new medium from a vacuum. So this number, N, will always be larger than 1. And basically all it is information about the speed of light in that medium. And so the index of refraction, if it changes, that means the speed of light has changed. And note here that the index of refraction does change with different materials, like between glass or water. It also varies with temperature, and it also varies with wavelength or frequency. So different colors of light will be refracted different amounts when they enter a new medium. We're going to see that. Then that is because the speed of light for each wavelength of light, for each color of light, is slightly different. And not only is N the ratio of the speed of light in vacuum to the speed of light in the medium, but we can prove here, you can follow it along yourself, that the N is also the ratio of the wavelengths, the wavelength in a vacuum divided by the wavelength in the new medium, which is represented by the subscript N here. Now that we've learned about the index of refraction, let's talk about Snell's law. Snell's law says that the index of refraction of the air times the sine of the incident angle is the same as the index of refraction of the glass times the sine of the refracted angle. Let's take a look at this a little closer. First of all, let's do a little geometry to show that this angle here, the incident angle, is the same as this angle drawn here, and that the refracted angle is the same as this angle over here. Why did I do that? Well, because I'm going to analyze these two right triangles. This is one of the rays between the wavefronts. Here's another wave between the wavefronts, this one in the glass, this one in the air. And we notice that they share a hypotenuse, which I've labeled L. So let's do a little analysis and geometry on these two triangles here. First of all, the sine of the angle is equal to the opposite over the hypotenuse. So lambda over L, and that's true for both triangles.
Solving those for lambda, this is what I get. And then I'm going to use my equation for index of refraction, solve it for v, and in my wave equation, for v, I'll plug in c over n, and for lambda, I'll plug in L sine theta. And that's what I get when I do that. And remembering that the frequency in the air is the same as the frequency in glass, I'm going to solve each of these for f. Set them equal to each other. The c and the l's will cancel out from either side, and I'll be left with my equation, that is Snell's law. Let's look at it with some numbers. So here's the example with the laser beam we saw a few minutes ago. Our incoming beam in the air came in at an angle of 46.5 degrees and was refracted to an angle of 33.5 degrees. You can see the readings here on this overlaid protractor. So I'll plug in my numbers. The index of refraction of air is 1.00 to 2 decimal places. It does differ from the speed of light in a vacuum, but it's beyond 2 decimal places. So we just use 1.00 for air. The sine of our incident angle, and 2, the index of refraction of water. That's what I'm trying to find. So that's what I'm going to solve for. And there's my refracted angle, 33.5. So when I solve for N2, I get 1.31. You'll see in your textbook that the accepted value for index of refraction for water is 1.33. Am I wrong? Well, let's ask ourselves, let's do a little error analysis. What if I measured these degrees and I was only off by half a degree? If you look here, you can see the width of the laser beam is almost a full degree by itself. So it's very possible and understandable that we could be off by half a degree. So I've done the calculation again, this time changing my angles by 1/2 of a degree, and I see that I come up with a new value of 1.34. The accepted value of 1.33 is between these two numbers, so I can feel confident that my experiment is valid within experimental error.